Hey everybody, Dr. A here, and in this video we're going to be exploring another example of a statically indeterminate axial system. So let's look at what we're given. Here we are given a hanger that's shown in this diagram, and we are being asked to compute the forces in the three rods. These are these three vertical rods. It says the beam is significantly more rigid than the three rods, and then A times E, which is the product of the cross-section area and the modulus of elasticity, is constant for the rods. So let's take a look at the diagram that we're given so we can make sure we can understand what we are dealing with. So we have this beam here. This is the horizontal member ABC, which is significantly more rigid than the three rods. Now, the reason why this is an important sentence is because when our beam is treated as significantly more rigid than the three rods, then that means that the beam's deformation is going to be very, very small compared to the elongation of these three rods. So basically what this sentence is telling us is that we don't really need to deal with the beam trying to bend, for example. What we're really dealing with is the elongation of these three rods. So that's the significance of that sentence. The next thing is that the cross-section area of these three rods is the product of the cross-section area of these three rods with the modulus of elasticity of these three rods is going to be constant, so they're going to be the same. Now, this horizontal beam is supporting a load of 0.15 KLF, that's kips per linear foot, and that's distributed over this 2-foot segment between points A and points B where these two rods are attached. And then we have a 3-foot segment that is unloaded that spans from point B to point C. Rods AD and BE are both 3 feet long, and then rod CF is 2 feet long. So how do we calculate the forces in these three rods? Well, let's go ahead and get started, and we'll see how we do that. So we're going to start with writing solution, and we're going to draw a free body diagram of the system, okay? So when we draw this free body diagram, we can show our beam here, and then on this 2-foot span, we have that uniformly distributed load pointing downwards that has a magnitude of 0.15 KLF, that's kips per linear foot. And again, that's over 2 feet. And then we have this 3-foot length that is unloaded. And so this is points A, points B, and point C. Now, what is happening at these 3 points? Well, we have these 3 axially loaded pin-connected rods. So you're going to have a vertical force develop in each of these rods, FAD, FBE, and FCF. Okay, now if we look at this system, the free body diagram of this system, we have 3 unknowns. We have these 3 unknown forces. How many equilibrium equations can we apply to this system? Well, your first instinct may say, oh, we have 3 equilibrium equations we can apply, but that's actually not correct in this particular system. Whenever you're investigating indeterminacy of a system, you have to look at the applicable equilibrium equations. So the first thing we should note is that sum of the forces in the x direction equaling 0 is not applicable for this system. Now, the reason for that is because in this free body diagram, we have nothing applied in the x direction. There are no forces happening horizontally or in the x direction. So you only have 2 applicable equilibrium equations. One of them is sum of the forces in the y direction equals 0. And we can write that out. We're going to have FAD plus FBE plus FCF minus 0.15 KLF times 2 feet equals 0. And we have sum of the moments about a point of our choosing equals 0. I'm going to sum moments about point A and take moments counterclockwise positive. So when I write this moment equation, I'm going to have minus 0.15 KLF times 2 feet times 1 foot plus FBE times 2 feet plus FCF times 5 feet equals 0, okay? So I'm going to call that force equilibrium equation in the y direction, I'm going to call that equation 1 because I want to refer back to that later on. And then I'm going to call our moment equilibrium equation equation 2. Again, I'm going to refer back to that here in just a few minutes. So if you notice, we have these two applicable equilibrium equations, but we still have 3 unknowns floating in between the two equations. Even though the sum of the moments about A, only 2 of the forces are showing up in that equation, but as a system of equations, you have 3 unknowns that are occurring here. So we need an extra piece of information. So our third equation, or our third piece of information we're going to use, is our compatibility equation. So we're going to use a compat equation as our third piece of information to solve this problem, okay? So how do we set up a compatibility equation for this system? Let's scroll up and look at it. How do you think we should do that? Well, compatibility equations are based on how things deform. And we have acknowledged that the deformations in the system are coming from the elongations of these 3 rods. So what we're going to do is we're going to draw a deformed sketch or a deformed diagram of this system, and then we're going to see what kind of information we can piece together from that. So I'm going to call this a deformation diagram. Okay, so the first thing I'm going to do is I'm going to draw a straight line segment that represents the beam. Okay, so here's point A, and then point B is 2 feet over from that, and point C is 3 feet over from that. Now, when these 3 rods elongate, are they all going to elongate by the same amount and the same way? No, not really. They're going to elongate based on the axial elongation formula, FL over AE. But if you notice, the lengths are different, and just look at this. Your force, your applied distributed load, 0.15 KLF, is on the left side of this entire system. So I would say that this beam is going to, not only is the whole thing going to move downwards, but you're going to have a tilt to it, okay? Point A is actually going to be deforming lower than point C. Okay, now this is an exaggerated view of that. Let's see if I can draw this a little bit better. There we go. So C is going to deform to a new point C prime. A is going to move downwards to a new point A prime. And then B is going to move downwards to a new point B prime. Okay, and again, I'm making a pretty safe assumption that the left side is going to deform lower than the right side because the load is applied between A and B. Now, just for completeness, I'm going to go ahead and just sketch on here my dimension lines that were given to us in the problem statement. This was 2 feet and this is 3 feet, okay? Now, what do you notice with this deformation diagram? Well, we can segment this out into simple shapes, and in particular, we can segment out a right triangle by projecting a horizontal line over from point C. So this dimension, the amount that C drops down to C prime is going to be called, we're going to call that little delta C. Okay, now the amount point A drops, of course, is little delta A. And then the amount B drops here is little delta B. My figure is getting a little messy, but just try to follow along with me. Now, what we're going to utilize is this right triangle, this little slice of a right triangle. And we can build similar triangles within this big right triangle. So the first thing I'm going to do at this point is I'm going to say this distance right here, which is one of the legs of that big sliced triangle, is going to be equal to what? Well, it's going to be equal to delta A minus delta C. How do I know that? Well, this rectangular portion drops down by an amount equal to this little delta C, okay? And so the remaining portion that drops down below that at point A is going to be little delta A minus little delta C, and we're left with this distance right here, delta A minus delta C. And then I'm going to do something similar over here. I'm going to have this distance, which is equal to delta B minus delta C, okay? Now, again, inside this right triangle, we can set up two similar triangles because we also, inside the larger right triangle, we have this smaller right triangle. So setting up similar triangles here, I can establish the relationship delta A minus delta C over what? Over the full 5 feet equals delta B minus delta C over 3 feet. Now I can do some rearranging here and get this in a more convenient form. So I'm going to multiply both sides of this equation by a constant, and I'm going to multiply it by the constant 15. Now you may be wondering, why am I multiplying both sides of this by 15? Well, if you want to avoid dealing with fractions of 1/5 and 1/3, you find a common denominator between the 1/5 and the 1/3, which is 15, and you multiply both sides of the equation by that. So if we do that, we're actually going to end up getting 3 delta A minus 3 delta C equals 5 delta B minus 5 delta C. Now we can combine like terms because we have a delta C term that shows up twice here, and we can rearrange this and get 3 delta A minus 5 delta B plus 2 delta C equals 0. So maybe pause the video, rewind it, do this on your own paper, make sure you follow along and you know where this comes from. So here's my next question for you. What are these delta values? Well, of course, they're elongations. They're axial elongations of those 3 rods. What's our formula for axial elongation? Well, it's force times length over area times modulus of elasticity, FL over AE. So what I can do now is I can substitute in my general formulas for FL over AE into these 3 delta terms, okay, because these are axially loaded rods. So substituting that in, I get 3 times FAD times LAD over AE minus 5 times FBE LBE over AE plus 2 times FCF LCF over AE all equals 0. Now, the problem statement told us that AE is constant. So if AE is constant in all 3 of these terms and the whole equation equals 0 now, we can wipe out this AE term. And do we know these lengths? Absolutely. We know the lengths of those rods. If you pause the video and rewind, or you look at your paper, you know you were given those lengths. So we can substitute those lengths in, and this equation becomes the following. We end up with 9 FAD minus 15 FBE plus 4 FCF equals 0. Again, pause the video, make sure you are getting these values that I'm getting. Now what I'm going to do is I'm going to summarize my equation system to solve, okay? So let's write a summary of equation system. Oh, and by the way, this equation right here, this is our 3rd useful equation. Remember earlier we labeled an equation 1 and equation 2. This is our 3rd useful equation that comes from this compatibility relationship. So rewriting each of these, we've got equation 1, which I'm going to rewrite a little bit nicer as FAD plus FBE plus FCF equals 0.3 kips. You may be wondering where that 0.3 kips come from. Well, if you go back to equation 1 that we, that first equilibrium equation, summing forces in the y direction, we had 0.15 KLF times 2 feet. There's your 0.3 kips. Equation 2 came from summing moments about point A. So kind of collapsing and rearranging some of the values in that equation, you're going to get 2 times FBE plus 5 times FCF equals 0.3 kip feet. Okay, so if you keep those units in there, you get 0.3 kip feet. Again, pause the video, make sure you know where these numbers are coming from. And then equation 3 that we just summarized, of course, is 9 FAD minus 15 FBE plus 4 FCF equals 0. Now, here's what I did here. I used my system solver in my TI-36X Pro, okay? So I use the 3x3 sys solver in the TI-36X Pro. It's a fantastic calculator. When you use this properly, you should get the following values. You get the force in AD equals 0.175 kips, which, as you know, is 175 pounds. You get FBE is equal to 0.109 kips, which is 109 pounds, and then you get FCF, which is 0.0164 kips, which is 16.4 pounds. And these are our final answers, okay? So these are the forces in the 3 rods. So that concludes this example. If you found this helpful, please hit like and subscribe. Thanks for watching.